Is Marco Miniaci. We are very happy that he made it and he could participate. So his work is on bio-inspired, mainly bio-inspired metamaterials, I would say. So Marco did his PhD in Bologna.
Yes.
Correct me if I'm wrong, I remember, but and then he traveled across Europe, and now he's in France, in Lille. But he did a postdoc in Torino, the Polytechnic di Torino. Then he was in Switzerland, and then in Le Havre, in France, and then he settled in Lille. And he just had ERC starting grant finance. So it's really a pleasure to have you here, Marco, and we'll let you talk about science.
Thank you, Giuseppe, for the very kind introduction and overall for the invitation. It's an honor to me to open these talks during this seminar. So thanks to the organizers. The place is really amazing. It has been my first time here in Arpino. I didn't know the city, but it's really nice. So thank you. I will try to speak about phononic crystals and metamaterials in the framework of bioinspiration, which is a topic that I've been working, let's say, in the last 7-8 years. So if we start from the context and the motivations that were pushing this work, we can say that in general, biological structures have always been a source of inspiration for solving technical challenges in many research fields, from architecture, aerodynamics, mechanical, civil engineering, and so on. Here I just report you one example. Maybe this is a little bit nationalist, but we are in Italy, so I reported the Leonardo da Vinci flying machine. So basically Leonardo was among the first that was trying to look at nature in the detail, to look at birds and how they fly, to try to make mankind flying. In that occasion, we know that he was kind of trying to conceive a structure that was flapping the wings as well. He failed indeed, because of course there is human beings have different bones density, etc. But I think that this is a very good and clear example of biomimicry, which means we look at a biological feature, at a biological mechanism, and we try to reproduce exactly the same for our purposes. We can, let's say, relax a little bit this and go from biomimicry to bioinspiration, in which we do not try to perfectly reproduce this mechanism, but we try somehow to take inspiration to solve our problem. And this is what we would like to focus. So our objective is to try to study and draw analogies from biological systems to engineer advanced materials with unique dynamic properties. Here I bring to your attention some other examples of bioinspiration. We are in the warm-up, so here there is, for example, in 1941, George de Maistral, he used to go around with this dog, and when he came back, he was observing that these bedrock burrs were very difficult to get rid of them from the burr of the dog. And so he decided to study at the microscope the sticking mechanism. He discovered that actually it was so difficult to get it from the fur of his dog because of this hook shape that was taking the hair of the dog. And so that's how he patented basically the velcrum. Another example is, for example, the Shinkansen bullet train, which derives from Japanese train engineering. So basically there was a problem that this train traveled around 200 miles per hour. At that time was one among the fastest, maybe now it is not. But the problem was that due to this high speed, when he was entering and getting out of tunnels, there were basically shock waves that were produced, and this was annoying people for a lot, even 1 kilometer away. So the idea was to try to find in nature an animal that was capable to travel quickly and smoothly between two fluids with different density. And basically, he inspired the design of his train to the kingfisher, which is able to catch prey in the water with very little splash. Here, just for fun, I reproduced some more funny bio-inspired examples. For example, here there is this bionic car Mercedes, which claims to be inspired by the boxfish, I guess for volume space. And some static applications. For example, here there is the external part of Beijing National Stadium, which is inspired by the way birds prepare their nest. So let's come now to some dynamic applications. And here I would just like to tell you a brief story about the long-standing battle between bats and moth butterflies. So basically here you can see a bat, and here you can see a moth butterfly in different position while he's flying. If we zoom, we can see that his fur has a specific, let's say, it's very specific, and we will see why. Before this, I just would like to bring to your attention, maybe you are all aware of this, how bats navigate and how they get prey with this mechanism, which is called as echolocation. So basically, they send ultrasounds. Then if there is an object, this reflects some echoes, which reaches the ear, right and left ear of the butterfly, and by some, I would say, signal processing, he can basically understand which is what is the map around his, and he can use this also for capturing prey. Here there is a movie in which basically there is moth butterflies, there is a bat that is coming, and with this echolocation, it is able to catch his prey. In the first 2 or 3 attempts, basically there are successful events. So the bat is capable to trap the prey. Maybe here he starts failing. More or less. Yeah, they are struggling a little bit. Yes, he saved in the end. But it's not this I would like to point your attention, it's this one. So here there is the bat that is coming, and clearly he missed the hit. So the question here is, what is happening? Is this simply a physical movement of the moth butterfly, or there is something more physical, more mechanical behind? And actually, what researchers have been claiming very recently is that there is some physics going on. So basically, if we look at the microscope, this moth butterfly fur wing, we can see that the architecture is very peculiar. And 2 keywords may comes up. The first one is that it is made by periodic structures. And the second keyword is that there is a hierarchical organization of this structure. Just to make it long story short, basically the moth butterfly wing behave as resonators that resonate into the specific frequency range that the bat uses to echolocate, so that when the bat receives the echo, it is not that strong and it cannot locate precisely his prey. So the take-home message here is that there are these materials which have these unusual behaviors stemming from the architecture rather from the materials themselves of which they are composed. So here I started putting the first keyword, which is metamaterials. I'm very happy to be the first to speak so I can define what is a metamaterial. So basically, you will find a lot of definitions. This is continuously evolving. There is maybe the most known is the one that tells that is a man-made structure, blah, 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 but I do not like it that much because indeed, recently we are going more and more in the direction of saying that nature indeed has already exploited this kind of mechanism. So I would just say that they are composites. We don't know if man-made, nature-made, which have a three-dimensional periodic or not periodic cellular architecture. This is very important, designed to produce a typical dynamic response to specific frequencies. Here, for example, I report a dispersion diagram. As you may know, in X, there is reported the reduced wave number, which gives us an information on the wave propagation direction. Then, here we have the frequency. We have these dispersion branches. At in a certain moment, we may have a total absence of dispersion curves, which means that this structure in this region cannot propagate energy from a point A to a point B. And these properties, this is just one among the properties, can be produced by the periodicity of the system. In this case, we have the dominant mechanism is the so-called Bragg scattering, and generally they are referred as phononic crystals because the unit cell size must be comparable to the wavelength. And we can also have these features emerging from resonances of our structure. And here there is the famous paper of Liu et al., in which they realized, maybe for the first time, this mechanical resonance by embedding steel spheres into a polymer matrix coated by a very soft rubber. Here, I would like just to go a little bit more in the detail on this bandgap behavior. So here there is a different unit cell in which we have, let's say, I call this flower-like, but basically there are 8 holes so that you can make inside a resonator connected by some ligaments, 8 in this case. We can calculate the dispersion band diagrams by applying periodic boundary conditions on the left and right so that this structure is infinitely repeated in the X and Y space. In Z, the structure is finite because this is a plate, so we have free boundary condition on the top and on the bottom. And here we can clearly see that we have a transmission drop where before we saw the bandgap, so the absence of dispersion curves. How we obtain this diagram? So basically we manufactured a full plate in which we inserted a finite square size of this type of unit cells. Then we excited elastic waves in E1 and we received in O1 and O2. And we can clearly see that, okay, at the beginning we have exactly the same energy level, then we have the drop of energy within the bandgap, and then more or less we reach comparable energy levels. Here is just to let you visualize what is going on. So on the left here we have numerical calculations. Here we have experiments with scalar laser Doppler vibrometer. We can clearly see that depending on the frequency of excitation, we may have the wave propagating inside our crystal or the wave being totally reflected by the crystal. Here I just, maybe I will skip this. I will just report the experimental verification of this one. So on this side, we have an excitation frequency which is outside the bandgap. So here is the piezo that is producing the elastic waves. Here you can see that although something, so this one was inside the bandgap. So you can see that there is no penetration of the energy measured by the laser inside our square. On the contrary, if we change the frequency on the same structure, we can see that now the waves are produced much higher. We can see that, okay, we have some scattering because of course there is no homogeneity anymore, but we do detect energy also inside the square ring. So let's now come to the second keyword, which is hierarchy. The question is here, why we decided to put our attention to the hierarchy. the main reason is because, so first of all, hierarchy for me means a material which has a structural organization at a different scale level. And I decided to focus on hierarchy because in static, but also in dynamic cases, we can see that hierarchy is often responsible for advanced properties, such as, for example, protection in the nacre, which has up to 4 hierarchical level, resilience in wood, which has up to 7 hierarchical level, and also filtering of light, for example, in diatoms. The advantages of using hierarchical structure from, okay, so this is French-Italian, so now I speak about French Eiffel Tower. The advantage of hierarchical structure in static fields is very well known, and basically it allows to minimize the material use while optimizing structural performance. So the question that I would like to start discussing with you is, what is the effects of hierarchy in phononic crystals and metamaterials in dynamics? If we give a look to the state of the art, I would say that this topic has been approached the first time in 2013. This is the most, the oldest paper I was able to find, in which a 1D crystal made of very soft, very thick, very soft, very thick layers organized in a recursively manner was designed. And this, as well as other type of approaches, for example, in lattice type structures, it was found the possibility of nucleate additional band gaps and control the wave directionality. However, in this case, you have to deal either with 2 materials, which is always a little bit annoying, that may produce defects, or you have to redesign at each time the geometry. And so going from one hierarchical level to another was not possible. What we propose here in a first attempt is to use continuous structures, to use only one material, to go in the direction of lightweight structures, and that they might be simple to manufacture. So by taking inspiration from the Cossinodiscus centralis biosilica valve, here you can clearly see that there is these patterns of holes, which is in an hexagonal manner, that is repeated at different scale levels. So we took a structure which is a unit cell made of polymer matrix with cross-like holes, which was reported in literature to be able to nucleate rather large band gap, to have negative dispersion branches, possibility of create Dirac cones, etc. So it's a really rich structure, and reproduce the same geometry by enforcing strict self-similarity. So basically, we take this structure, we do not change nothing, but a scale parameter. So here we scale it by 20 times, and we reproduce the same cross-like hole. Just to give you an idea of how it looks like and of its simplicity, this is a 3D printed structure. So you can see here the big cross, and then you have this little cross that are at another hierarchical level. I don't know if you want this to circulate or not. So concerning calculation methods, they are rather standard. So we proposed linear elastic models where we have 2D wave equation, block expansion theorem, etc. We end up in this case with typical dispersion equations that we can solve with standard codes. We can also consider the case of linear viscoelastic materials where we have to introduce a frequency-dependent elastic moduli, and this will lead us to non-typical dispersion equations. And we used the most simple approach where we have only one viscosity parameter introduced as a complex wave number K star. Basically, this is the Kelvin-Voigt model. So here, this is the calculation of the structures that is turning around. You can see that there are two crosses. So the green one, this one, which is the small unit cell or the regular unit cell, and the big one, the red, which is the hierarchical one. Oh, nice. So if we compare the dispersion diagrams of the small or regular structure and the one with the hierarchical level, we can see that there is a partial conservation of band gaps. Why I talk about partial conservation? Because basically here you can see the dispersion branches in black, then you see a big band gap in gray, and here you can see this blue these blue rectangulars basically are a plethora of dispersion curves that are superimposed. Indeed, if we zoom, we can clearly see that this is distinct dispersion branches, but in the whole frequency range that we examine, they just stick one to another. But in red, I reported the band gaps. So you can clearly see that the lower limit and the upper limit more or less coincides. Why I say more or less? Because if you go here and you zoom here, you can see that these branches are rather flat, which means group velocity extremely low, thus corresponding to rather localized modes. And with a little bit of viscoelasticity, which is present in almost all materials, these modes after 2-3 unit cell basically will be evanescent. If we give a look on the other hand, the second interesting thing is that we can open band gaps at low frequencies with a structural weight reduction of 45% in this case, because if we give a look to these frequency regions, we can see that in the regular structure we have dispersion branches, so basically wave propagates, can propagates, whereas here we introduce some additional band gaps. If we try to get a little bit more insights about what is going on here, and we compare a 2-unit cell of the same size, but in the first case of homogeneous material, and the other case, let's say the microstructured material, we can see that these curves here basically corresponds to this one, which have been flattened down of approximately a factor of 3. So here the mid band gap frequency is 24, here is 8. And we can also observe that at the low frequency, basically we have self-similarity of mode deformation, which do not feel the microstructure. Here is just an animation. If we would like to get why we had this 1/3 shift, we can produce a mass spring model explaining this band gap lowering, where we consider this as the mass and the ligaments here as the connecting springs. We calculate the mid band gap frequency as the ratio of the root square of the effective stiffness divided by the effective mass. And if we reproduce the same calculation by introducing the hierarchy and we take the ratio of the two, indeed we end up with a 1/3 reduction. So basically here there is nothing exceptional. We simply changed mass and stiffness. We had some additional benefits of opening new band gaps, but we altered mass and stiffness. Some experiments on a different sample, which is made of aluminum, indeed, because polymer at very high frequency can become very rapidly very dissipative, and it was quite difficult to measure at hundreds of kilohertz. In the aluminum, things went a little bit better, and indeed you can see that, maybe I'm annoying you, here you can see a little bit better. In aluminum, we could see a little bit better what was going on. So here you see the dispersion band diagram in which the dispersion in the lower frequency regime, where the dispersion branches are color-coded according to this factor, which basically takes into account the integral over the volume of the displacement out of plane with respect of the total displacement. Clearly, this parameter goes to 0 when the mode lies in the plane, whereas it goes to 1 when we have flexural modes, so out of plane deformation. And here you can see that the measurements were in good agreement with what I call the partial band gap, so band gap only for out of plane modes. Here you can see them. And we were also able to catch the complete band gaps where there is no dispersion branches irrespective of the polarization mode. We did the same thing at the very high frequency here, and we can also see that in this frequency regime we have a strong attenuation of the transmission, so 40 dB. And let's get some insights on what is going on these two different frequency regimes. So at the low frequency, we can clearly see, if we perform a frequency domain analysis, we can see that by sending a plane wave from the left, let's say the big unit cell is the one responsible for the backscattering of this wave. So you can see that the microstructure is not felt when you arrive at half of this structure, since this is Bragg scattering, you go back. If we do the same for the hierarchical level, of course we have to zoom a little bit, and what is going on is that the half of the small unit cell is producing the backscattering. So here I would like to tell you that the same mechanism is proposed at different scale level, which is introduced by the hierarchy. So we started a little bit enjoying this idea. We said, okay, but in nature things are not perfectly repeated. There are more or less the same unit cell that repeats. So we decided to relax the strict self-similarity, and indeed this allowed us to introduce further functionalities in our structure. For example, here we were able to replace the connecting region by a stretched cross-like hole, which is called, which is known in literature as inertial amplification mechanism. So basically here, due to the fact that the stiffness here is very, very limited, here, here, and here, this structure will deformate like a mechanism, a mechanical mechanism, and this will produce an effective resonant mass, effective I say, very high. So here we can shortcome the problem of locally resonant metamaterials, which generally requires very heavy masses. This is the unit cell of the new hierarchical non-self-similar structure. And just to let you know what is going on, here I reported an illustrative band diagram. Here we are in logarithm scales, and you can see that the white rectangles corresponds to mainly propagative regions, so basically where dispersion branches are present. Then you have blue rectangles are band gaps. And you can see that also in this case, of course, we have the same features that occurred before, but now, very interestingly, we have that some specific regions of our structure is responsible for the activation of different mechanical, different mechanism and at different frequency ranges. For example, in the very low frequency regime, we have the inertial amplification localized in the connecting regions going on. In the mid frequency is the whole structure behaving, let's say, deformating entirely. And at the very high frequency, we have the localization at the small crosses. Here, just to show you some results. So here we had to put some wires to reproduce the free boundary condition, and then we attached a shaker, but the structure was becoming very, so here there is a, we verified just for the low frequency regime, which was the most challenging, and you can see a good agreement between bandgap and experiments. These additional peaks may be to the fact that the calculations were made in 2D plane strain. Here we may also engender some out-of-plane displacement, but in any case, we are inside the bandgap. So what is going on here is already 1 or 1.5 order of magnitude lower. What I would like to bring to your attention is here, the details of this fabrication. These are the hinges. And basically what we realized is that the structure was becoming extremely compliant. So Houston, we have a problem in the sense that, okay, we are obtaining more and more large bandgap. We are going lower and lower in frequency, but everything is done at the expenses of rigidity. Let's say for practical application, having extremely compliant devices could be not a problem for, I don't know what domains, but let's say if we remain in the civil, mechanical, engineering, this might be a problem. So the great unsolved challenge up to now is that we do not really know how to decouple the alteration of the stiffness and the frequency at which we obtain the attenuation in phononic crystals or metamaterials. Here we decided to do a step behind. I'm just checking what time is it. And we decided to lower our level of inspiration and give a look to what is known in literature as chirality and tacticity. So we see that in biology, amino acids are the primary structural unit of proteins, and they all, except glycine, are chiral. So chiral is a word that comes from Greek, which means hand, and this means that they are one the mirror image of the other. So basically, we cannot superimpose our hands by making translations or rotations. In statics, this also has been investigated. There are some groups that produced these chiral structures made of circular geometry with bent ligaments, and they observed that this structure under compression originates a twist. There are some other examples of chiral phononic crystals in literature. This is, for example, a locally resonant structure made of rubber and spiral and chiral ligaments. The propagation is, and this is another example made of the same structure. Here is the Venn diagram. What I would like to bring to your attention here is that the wave propagation and the structural rotation induced by the chirality are in the same plane. So basically, the wave comes from here. The structure here, the resonator, starts to rotate. The chiral ligaments get deformed, and the wave propagates in this direction. So the propagation direction and the deformation is in the same plane. Then I will maybe not spoil Giuseppe's talk, that he will talk about chirality as well. And here we decided to have the wave propagation in the z direction and the rotation in the orthogonal plane. We started from this concept of single oscillator with 1 degree of freedom. So this is the theory. We have a mass spring system with rigidity K and mass M. We tried to reproduce this by putting a rather thick disk connected by straight ligaments, which in this case are parallel and orthogonal with respect to the disk. This system can only translate in the z direction. Then we decided to make an angle with respect to the vertical of these ligaments, and we can see that if we look at the frequency response function, we already can see that we have some more rich kinematics, because in the same frequency region, the single oscillator resonates and then start doing things at higher frequencies, whereas keeping the same stiffness, so basically even if here we put an angle with respect to the vertical, we changed the material and the stiffness so that the parameter K is exactly the same. Here we can see that we have a more rich frequency response function in the same frequency regime. And the wave propagation and the structural rotation induced by the chirality lies in orthogonal planes. Then we decided to see, okay, let's now see how to concatenate these materials. And in stoichiometry, we have the possibility of putting them in a symmetric way, so the so-called isotactic arrangement, where we have R1, R2, R1, R2, as the chiral centers simply repeated. We can have them in a syntiotatic way, so they alternate, so we have R1, R2, then R2, R1, and once again alternating R1, R2. And then of course, we can have atactic arrangement, which means simply periodic, but we will not focus on this. With our twisted resonator, we made now this isotactic arrangement. So here we can see that now the unit cell became a unit cell hosting two resonators, but in the isotactic case, we simply put them one close to the other, as done in literature so far. And here the rotation of the ligaments is always the same, clockwise or counterclockwise. Whereas in the syntiotatic arrangement, we have one clockwise, one counterclockwise, clockwise, counterclockwise. And the unit cell is still this one. The very interesting thing is that here, this structure, under mechanical strain, these two structures are identical. You can clearly see from the experiments that the deformation path, here is one load and the load paths, for the two structures are the same. Here we registered 14.78 Newton per millimeter, here 1469. Whereas, from the dynamical point of view, these two structures are completely different. The one on the left, in the low frequency regime, propagates waves without problems. The second one opens a rather large sub-wavelength bandgap. Here also the curves are color-coded because in accordance to the curl of the disks, this allows us to distinguish modes that really propagates into the structure from these modes which are rather localized in the ligaments or in the disc. And here there is the experimental measurements of these two devices. So this you can see that is the isotactic. We always turn in the same direction. Here we have alternating clockwise and counterclockwise rotation. The dispersion, the frequency response rather agree well with the calculated band gap. And finally, I would like to talk to you about this problem of tunability, because up to now, okay, we have designed these systems, but once that the design is finished, once that the structure is produced, these band gaps or these properties are fixed in frequencies, whereas in some cases it could be beneficial to let them vary with the frequency at our will. So there is a lot of work done on this actually, which are called periodic systems with adaptive elastic properties. And the aim is to have reversible tailoring of the dispersion diagram of the structure. You can see here that there are several approaches. Maybe the most used and known is using the piezoelectric materials. Here you have a slab of shunted piezos, and you can see that by turning on and off the piezo, we can basically pass from a band gap behavior to a passband behavior. Other approaches included temperature and magneto-based techniques or actuated polymers via electromagnetic waves. Here, for example, there is the effect registered of terphenol D, which has giant magnetostrictive properties. This means that under strong magnetic fields, it can vary up to 50% some of the elastic constants. Of course, other approaches a little bit less complicated may involve the application of external mechanical load. Here you can clearly see the shift towards higher frequencies of the dispersion branches or lower frequency if we apply compression or traction. I apologize, it's I guess that you cannot read. However, in all these approaches, there is the complexity of the practical implementation because we have the need for additional electrical wirings, mechanical stability in the case of mechanical forces, physical contacts required, and so on. So we took again inspiration from nature, and we observed that in nature there are these shape-changing materials which are rather widespread in nature. For example, here I bring to your attention the behavior of pine cones, which they close when the scales go wet, and they open when they go dry. Here you can see what happens. Another possibility is the so-called phototropism. So basically is the ability to track a light source and align to it, for example, sunflowers. And we came up with the idea, okay, let's try to make a metamaterial which is responsive to light, so that changes its properties when somehow we illuminate it. Here there is an example. So this is the specimen that we fabricated. It is made by a slab with some pillars fabricated with digital light processing 3D printing, also known as two-photon lithography system. The polymer that we used, I'm not an expert in this, so please don't ask a question on this, but is the so-called BEDA, bisphenol A ethoxylate diacrylate. This is the unit cell, and the experimental setup is the following. So we have a piezo actuating and producing elastic waves on our structure. We have the laser, which is illuminating a specific region of our structure. So this is the illuminating laser. And then we have the scanning laser, which is a traditional scanning laser Doppler vibrometer with which we measured the response function. When the structure is not illuminated, we can clearly see that as far as we register the signal in the different number of pillars, we open the band gap, which is in good agreement with dispersion curves. Then we started illuminating our sample, and if I don't remember bad, it's light in the green or in the blue regime. We observe a photo softening in a single pillar. And we can clearly see that we have a photo shift of the frequency of resonance of our structure. This can be seen in this diagram, where we have the frequency, the light intensity of our illuminating laser, and the spectral weight. You can see that as we increase the light intensity, we move to lower frequencies the peak of the resonance. And here there is also a full wave field reconstruction, which indicates us that at the same frequency we have a totally different deformation shape of our structure. Here we fixed the illumination intensity of the laser to 150 milliwatt. Once again, we have the frequency, the transmission, and the time. So we can see, we can recognize in this frequency region from 70 to 90 a band gap. Then the illumination is turned on at 100 seconds. We need some time our sample to soft, and we can see that once we waited sufficient time, we have a clear band gap enlargement. Here we go from 60 to 95, whereas before we were 85, 70. Then we turn off the laser, the illuminating laser at 260 seconds. We wait another little bit, and we can clearly see that we recover the same band gap that we had before the illumination. This is just a vertical cut to show you the band gap enlargement in terms of frequency and spectral weight. We also performed other type of measurements. So here, for example, we put the light off and the light on. We put the vibrometer laser as scanning, so basically it was moving along our sample, whereas the excitation laser was fixed into a spot, so here in this pillar. The waves were excited here, and we can see that the two maps are different. So at the beginning, of course, we have more or less the same. Then we start from this on, where we put the illumination, we start having a different width of the band gap. This is also confirmed by this other scan, where we can see that in the extreme case, we can go from 16 kilohertz width band gap to 38. In this case, we made the measurements in the other case, in the other way around. So we fixed the excitation on the first pillar, and we fixed the laser vibrometer with which we were acquiring the results, and we moved the laser which were illuminating our sample. This was also possible to produce to give rise to photo-switchable elastic filter. So in this diagram, once again, we have time, we have amplitude of the wave, and we have laser power. So here you can see that when we turn it on, we need to wait some time, but then quite rapidly we go down in the transmission. We turn the laser, the illuminating laser, off. We wait a little bit of time, and we go up in transmission, and we can enjoy doing this several times. Here there is, I guess, 50 or 100, I don't remember, cycles, and you can see that it is rather stable. We can also decide the amplitude. So if we do not use 200 milliwatt as the laser power, we can decrease our transmission, but only of a little bit. Or we can increase further the illuminating laser, and we can decrease further the transmission, or even further. So this is just to conclude. First conclusions, I will annoy you another 10 minutes. So we highlighted the points of strength and weakness of bio-inspired hierarchical metamaterials, but I think that this is rather a promising research topic. Of course, there is a lot to say here in terms of numerical modeling, because as soon as you increase the hierarchical levels with ordinary finite element approaches, simply the calculation costs become unaffordable. We studied the effects of tacticity in chiral structures and the possibility of tune the response through light. Here I just would like to talk about an application of these metamaterials where we observed a spectral flow of localized mode in these bandgap structures. So as you may know, the confinement of waves is of great interest in all wave-based technology. Here we have let's say a summary of all the possible types of localization. So here there is the frequency, here there is the space, this is a gap, and this is this is a gap, the white is a gap, and the blue is a propagative region. We can have, if we excite at a certain frequency omega our structure, if we are inside the propagative region, we have extended state, so basically the deformation of all the structure is involved. We can have a local resonance mode, so we have a localization of mode in space, but due to some leakage, the energy will anyhow propagated in the structure. We can have a mode which is very localized in space inside the spectrum, or we can have a confinement in space within the bandgap. And this is what is called a regular bound state, and what we would like to achieve in our structure. In literature so far, most of the approaches relied on contextual modification. So basically you take your structure, which is made of unit cells. You remove one unit cell, so you make a defect, and you can see that you can indeed localize a mode. You can see here the wave field reconstruction, and you can see here the transmission. Here, another example inside the band gap in terms of dispersion bands. And here, another example dealing with the so-called topological wave protection, in which you can localize a wave mode between an interface of two different materials. Here you can see that this is dark blue and this is light blue, but in any case, due to this different structure, you can guide the wave through a certain pattern without experiencing backscattering. So this is so-called ordinary topological protection, which, however, involves modification over the whole structure. In that, indeed, we have the need to design a domain A and a domain B. Here is the example, for example, here is the example where we inverted the direction of these blind holes or the radius of the lower and the top hole. So the feeling is that there is no general theory that was guaranteeing the possibility of localized mode within an arbitrary location with minimal geometrical modification. And this is our challenge. We start from a simple structure, so a mass spring system. Here are the masses. This is in yellow the unit cell, which is made of two identical masses and two different springs. So if you look at here, you have more stiff, less stiff, more stiff, less stiff. And we try to introduce a defect here in a space, and we try to achieve a localized mode. This is, as you may know, in monatomic chains, nothing special happens. So this is the reason why we choose at least two different stiffness. And depending on how long is this finite structure, we may end up to have our eigenfrequencies over these two branches. The idea here is to count the modes. So basically, we take our mass spring chain to avoid the trivial localization at the edges. We make it in the form of a ring. And then we have this K and delta parameters. The possibility is either K is bigger, either delta is bigger. We put ourselves in the case of K bigger than delta, and we make a limit the reasoning. So we say we put delta to 0. We get rid of all these gray springs, right? If we calculate the eigenfrequencies here, we have omega equal to 0 with n multiplicity, and omega equal root square of 2k divided by m with n multiplicity. Nice. Now we introduce our defect as a parameter lambda, which modulates the stiffness of our spring k or delta. If we start from modulating k, we put lambda to 0, so extreme case. We do the same thing, we send delta to 0, and we have this situation. In this situation, we will have n plus 1 omega equal to 0, because now we have one spring less but two mass more, and omega is equal to n minus 1. Since we can vary lambda in a continuous manner from 0 to 1, basically the only way is that there is a spectral flow, so a mode is migrating from this region, from this bulk region, to this other. Here I would like to recall you that this is not a dispersion band diagram, but this is the lambda parameter, and each of these are eigenfrequencies. So for 0.2, these are all the eigenfrequencies, etc. We do the same by changing the stiffness of delta, and we can see that if we get rid of this spring and then we send delta to 0, basically we do not achieve any change, because we still have multiplicity of omega equal to 0 and omega equal to root square of 2k divided by m. So no spectral flow here. And this is a rationale that allows us to know a priori, once that we introduce a modification, a structural modification in our structure, where we can, if we can achieve, and where we can achieve a mode localization. This is the structures that are manufactured, and you can see that we have 10 samples. Here we vary the radius of this. We go from 1 to, we cannot go to 0, but this is the most thin. We have two families of these structures because we want to test the case of k bigger than delta and k smaller than delta and show that one case is non-trivial because give rise to the localized mode and the other case is trivial. Concerning the methods, we used analytical and numerical calculation plus scanning laser Doppler vibrometer. We excited our sample in the central mass. We put a laser here to be sure of what we were injecting in our system, and we acquired the signals on all these masses. We decided to put ourselves in the dispersion band gap because so to avoid all the possibility of emerging of other modes and clearly identify the localized mode. These are the numerical results. So here, once again, these are not dispersion diagrams. These are the variation of the parameter lambda for the non-trivial structure and for the trivial one, and these are the eigenfrequencies. And you can clearly see that we have a mode migration. So from here, if you count, these modes here are n, and here they are n minus 1, because one mode has migrated, and here we have no migration modes. This is the experimental results. The agreement were quite nice. We were happy about this. And here, this is the mode shape reconstruction. So in blue, the analytical model, with the dots, the experiments, and here the finite element models. We can see that in the trivial case, in both cases, here and here, the mode does not exhibit any specific localization. Whereas in this other case, when the mode is inside the band gap, we have a clear localization, also visible from the numerical models here, in correspondence of the hinge, the modification of the hinge. Then the modes become again, let's say, deforms again the whole structure once it reaches the other bulk region on the top. Just some little bit of mathematics, very little. The prediction of this mode can be obtained by the so-called integrated density of modes, which is the analogs of what is the Chern number in the topological systems. So you take your structure, you put the defects, you divide your domain into two parts, the one on the left and the one on the right of our structure, and you calculate this double sum. Basically, these are mode shapes. And you can end up with an integer or with a fraction. If you end up with an integer, you know that there is no localization, so you are in a trivial structure. Whereas if you end up with a fraction, you are guaranteed the presence of a localized mode. We did this on our experiments, starting from the pristine structure. So here, lambda, you have to set it to 1. These are the frequency response functions registered at the different masses, identifying the different modes. And if you calculate this value, you can see that in this case, so k bigger than delta, we have a fractional number. So here, we will be sure that there will be a localized modes. Here, we have integer. These are experiments, so they are not perfect, but fair enough to say that this is fractional, this is integer number. To sum up, we have this unit cell made of two masses and different identical masses and different springs. We open a gap, we vary the rigidity of a specific spring, and we are guaranteed that we open a spectral flow. For the sake of time, I will skip the case of 2D elasticity. I just would like to tell you that, very briefly, you can put the mass spring system in the ring of an hexagon, repeat exactly the same procedure, go from the discrete to the continuous model, and introduce the defect as slits in our springs. We can have a short slit or a long slit, and also in this case we can observe that in the non-trivial you have the spectral flow, and in the trivial one you don't. Here the magenta colors indicates out of plane displacement, the cyan one the in plane modes, and here are the deformation, the localization of the mode, and in the trivial case, no localization. So just I have to thank all the people I had the chance to collaborate and from which I've learned a lot and with which I have been exploring all these topics. And of course, you for the attention, and once again, Giuseppe, for organizing this very nice workshop.